Hi, I'm Shomo. The human brain has billions of neurons. However, we perform tasks using only a few concurrently active neurons. Moreover, an activated neuron inhibits the activity of its neighbors. Selfless learning exploits these neurobiological principles to solve the problem of catastrophic forgetting in continual learning. The paper introduces a regularizer which penalizes concurrently active nearby neurons. This results in a pool of free neurons which can be utilized by upcoming tasks, thereby creating a sparse and decorrelated representation. In this paper, we ask a basic question. Can the selfless learning idea be used to improve the accuracy of popular deep networks in the usual classification setting? By usual classification setting, we mean that we have one classification task and have access to the complete training dataset. We hypothesize that easy samples would require less number of neurons to be learned, thereby leaving the harder samples more neurons to work with. This idea helps us answer our question. We use uncertainty sampling to partition the training dataset into easy and hard samples. This is a popular strategy in active learning. For a channel C, AIC superscript M is the activation for location IC and example M. So the first regularizer ensures neural inhibition for easy samples, while the second regularizer prevents representational overlap between easy and hard samples. Enable richer representations for complex tasks. We constrain IC and JC to take values from the same column or row of the feature map. Also, since our characterization of easy and hard samples depends on an arbitrary threshold, alpha makes sure that if the hard sample is similar to the easy samples, the penalization is less. We also employ a curriculum learning type of strategy where in each training epoch we first train our network on the easy samples followed by both easy and hard samples. Since we use all of our training data in each epoch, this strategy is different from the usual curriculum learning. There are some practical considerations in our method, like where to apply our regularizer and how much easy samples to suppress. As for the result, our method outperforms cross-entropy on three fine-grained datasets and on ImageNet. It should be pointed out that our method performs particularly well on fine-grained datasets, possibly because of interclass similarity. In order to demonstrate that our approach can be combined with other learning paradigms, we plug it into a popular curriculum learning method. We also performed thorough ablation studies on different sample selection strategies and show how each part of our method works. Additionally, our regularizers promote lower mean activation values than vanilla cross-entropy.